街を包む Midnight Fall 孤独なシルエット動き出せばそれは紛れもなくやつさコブラ Leaving me blue コブラ Missing you too コブラ Only few memories after you 背中にまといつく陰りは男という名の物語許されるはずもない Peace and love
Okay, welcome back, everybody. So, yesterday, we ended with an application of Polya's enumeration formula. The idea here was the following. So this is, say we're looking for the pattern inventory for 4 beaded necklaces using 3 colors, red, green, and blue. So our pattern inventory for D4 we found was the following. So this is directly from here. I'll flash it back on the screen. Sorry. What I'm writing here is the cycle index by Polya's enumeration formula. This is going to give us the pattern inventory when we plug in the right thing here. So here, this is our definition of cycle index, and this is our derivation that the cycle index for the dihedral group on 4 vertices was this thing, this polynomial here. So I'm just going to copy this so it's on the same sheet. So this is 1/8, that 8 coming from, of course, the fact that the size of the dihedral group on 4 vertices is 8. So it's 1 over the size of the group, 1 over 8 in this case, times this polynomial that we found was x sub 1 to the 4th plus 2 times x sub 1 squared, x sub 2 plus 3 times x sub 2 squared plus 2 times x sub 4. Now, by Polya's enumeration formula, the pattern inventory we seek is the following. So this is pattern inventory for 4 beaded necklaces, discounting this dihedral group on 4 vertices, the symmetries coming from that. So these are rotational and reflection symmetries using 3 colors, red, green, and blue. By Polya's enumeration formula, this is computed by plugging the sums of the corresponding powers of R, G, and B into these slots. And what I mean by that is into the first slot of the cycle index, I plug r plus g plus b. Into the second slot, I plug the sum of the squares. Into the next slot, I plug the sum of the cubes. And into the last slot, I plug the sum of these fourth powers. Now, yesterday I wrote out what the final form of this is, but there may be confusion as to what it was that was actually done here. So I cut out a lot of the all of the algebra that would have been done to arrive at this. But let's see what I mean here. So writing this out, this would be 1/8 times into the first slot, the x sub 1 slot, goes r plus g plus b. So this would be 1/8 times r plus g plus b to the fourth, plus 2 times r plus g plus b all squared, times x sub 2 being plugged in the second slot is the sum of the squares here, so r squared plus g squared plus b squared, plus 3 times x sub 2 squared, so this would be r squared plus g squared plus b squared all squared, plus 2 times x sub 4. X sub 4 is this last slot, and what's getting plugged into that last slot is the sum of the fourth powers. And now, if I want to answer questions, if I want this to be a proper pattern inventory where I can actually just read off the coefficients of all these powers, then I'm going to have to obviously do some algebra here to reduce all this and make it reasonable. Okay, so notice I could use the multinomial theorem for this trinomial here to do this. If for multinomial theorem, I'm going to get like Pascal's pyramid, if you like, right? And unpacking that would let me expand this thing in a nice way if I wanted to do it like that. One thing to check, though, if this is actually going to be a pattern inventory for 4 beaded necklaces using these 3 colors, what does that mean? It means that every term in this should be a degree 4 term, right? What do I mean by that? This is a 4 beaded necklace, so pattern inventory and looking at its coefficients allows me to see the count on these objects where I'm using a specified number of beads here. I'm using from each color, but in all cases, these are 4 beaded necklaces. And so I'm not allowed to use a number of red, green, and blue beads that would give me a necklace that has either less or more than 4 beads. So necessarily, every term in this would have to be degree 4. You can check very quickly before you've done any expanding that this is going to, in fact, be the case. So by the multinomial theorem, if you expand this, every term in this is going to be degree 4. It's going to have, combining the powers of R, G, and B, that's always going to be 4 in each term. And you go through each of these terms and you see the exact same thing is true. So here, all these are degree 4 terms. All these are degree 4 terms. All these are degree 4 terms. You can just see because there's only 3 terms there and all of them have degree 4. So that's one thing. So that works at least in that sense. Notice also I have this 1/8 here, but I am going to, so after some algebra, I'm going to write out what this actually is. This is what I wrote down yesterday that might have been slightly confusing. So after doing some algebra, what I get is r to the 4th plus g to the 4th plus b to the 4th plus r cubed g plus r g cubed plus r cubed b plus r b cubed plus g cubed b plus g b cubed plus 2 r squared g squared plus 2 r squared b squared plus 2 g squared b squared plus 2 r squared gb plus 2 r g squared b plus 2 r gb squared. Now, there's a couple of things to note here. Obviously, because this, in all of the coefficients here, I get positive integers, right? Because this is supposed to be a count on the number of ways to build a 4 beaded necklaces using exactly the specified number of colors here. This 8 is going to have to ultimately divide anything in this algebra showing up here. So for instance, let's look at these terms. Like the r to the fourth, g to the fourth, b to the fourth terms. Those have coefficients of 1. So then here, whatever the coefficients show up in this algebra here, there needs to be 8 total. Let's just check that that's the case, right? So I'm going to get, we'll do it for r to the fourth. So I get an r to the fourth here, that's 1. Okay, I only get 1 from here. I get 2 from this middle term, because I'll get an r squared showing up in this expansion, then times that r squared times 2, so that's 2. So 1 plus 2. Here I'm going to get 3. I'm going to get a single r squared term, and then it's going to be 3 times that. So 1 plus 2 plus 3. And then lastly, I have 2 times r to the fourth. So in total, that is exactly 8 r to the fourth divided by 8 is 1 r to the fourth. That is how all of these work. You might look at this and say, wait, I don't need to do this awful algebra here because I can just count each of what these coefficients would be knowing what the pattern inventory is supposed to be. Okay, and that's true for this type of problem. It's easy because there's not that many beads. So 4 beads, 3 colors. If I were to ask you, okay, how many non-equivalent ways are there to build a 4-beaded necklace using only red? So all 4 beads are red. Well, you would say 1, obviously, but that's the coefficient here. How many ways are there to do it if you have 1 red and 3 green, for instance? Right? Well, 1 red and 3 green, there's 1 non-equivalent way of doing that for a 4-beaded necklace here because we're using the dihedral group. So 1 red and 3 green, that's exactly here. That has the coefficient of 1. So you could go through each of these powers and just very quickly come up with the count yourself, basically, because it's a small picture. But the idea here, one, that would just be you computing the pattern inventory like on your own and not using the enumeration formula. The fact that we can start here and just apply algebra to crank this out without thinking about how to count these things or what the count might be, that's the power, because this same approach, this exact same algebraic approach, the algebra involved might be awful, it might be nasty, it might be something that doing it by hand is borderline impossible, so you would rely on a computer, but hey, that's not a problem. All right, that's perfectly fine. The point is that there is this deterministic algebraic process provided by this. No thinking here needed once we have plugged this in. Now we get the coefficients spat out for us. That's the power of the enumeration formula, and that's the point. The point is that we could apply this to a situation that's much nastier, like the one we also did yesterday that had that extremely long pattern inventory that I showed on screen for the 20 beaded necklace. Okay, so that's the key. That's the point. So if you were to do all of this algebra, this is exactly the thing that you would get algebraically, and by Polya's enumeration formula, this is giving us the pattern inventory. You can check in the reverse direction that in fact these coefficients match up. There should be 2 non-equivalent 4-beaded necklaces that we can use or that we can build that use exactly 2 red beads and 2 green beads, for instance. And it shouldn't matter if that's red or green. Red, blue should be the same. Green, blue should be the same, right? So you can ponder that. You can come up with that example on your own if you like, showing those 2 non-equivalent colorings. But anyway, I wanted to do that just to kind of reinforce what we'd done yesterday and not leave you hanging on a little bit of confusion. So that's the deal. All right. Moving on. I wanted to kind of start a what should I say? Should I say a survey or maybe like an overview of some interesting numbers? I think it's probably a good thing to think about in a combinatorics class about interesting classes of numbers. We've already seen a few that pop up a lot. Of course, the binomial coefficients, the Catalan numbers. But we have some other named numbers that we haven't really dealt with yet. And so the first thing I would ask you is to consider the question. Let's say that King Arthur is going to divide his knights into committees. And so instead of one round table, there are going to be K round tables. So how many ways are there to seat in knights at K round tables? Okay, if each table can seat any number of knights, no table is empty, and we count two seating arrangements as different only if some knight has a different neighbor on his left side in each one. Or right side. Okay, in each one. Okay, so pause for a second. Seems like a very long-winded question. So, how many ways are there to seat n knights at k round tables? Each table can seat any number of knights, but we can't leave any table empty. And we count two seating arrangements as different only if some knight has a different neighbor to his left or right side in each one. Okay, the tables are identical here. So there's no distinguishing between the tables. They're all identical round tables. So which particular table is occupied by which group of knights doesn't matter. So once a group of knights is assigned to a table, we must account for all possible seating arrangements there. Maybe I'll include that, right? So the tables are identical, thus once a group of knights is assigned to a table, we must account for all possible seating arrangements there. Right? Well, that's a question we actually have dealt with before, of course. That's the That is the question of this first question that we investigated when it came to counting with symmetry, which is King Arthur seating in knights around a single round table. Okay. So, of course, recall from this consideration, there are, say, m minus 1 factorial different ways to seat m knights at a single round table. Right, this is the first symmetry question we answered using Burnside's lemma. Okay, there are combinatorial ways to see it, so the Burnside's lemma is not strictly required, but that's how we did it because we had an idea we were going to use that to go further into Polya's enumeration formula and to deal with more complicated sorts of questions. Okay. All right. And so, how do I deal with this question? All right. So what's the idea? Let's come up with some notation that might help us figure out what it is that's going on. All right. So we have n knights. We can label those knights with the integers 1 to n. Okay. And so we'll say that these knights, we might label them like k sub 1 through k sub n. So a seating of knights around one table we'll say a seating of m knights around a table is something like now I'm really putting the labels on after the fact. Okay, so don't get confused that I'm saying that any seating has to look exactly like these if we've already labeled the knights, but whatever, we've assigned a seating of m knights, and then we can label the knights in that arrangement 1 to m. Okay. Now, of course, using parentheses here to denote this seating, and we're even like kind of baking in cycle notation here. Of course, you're noticing note an equivalent seating is the following. So, like for instance, let's say I started with k sub 2 here, k sub 3, up to k sub m, and then k sub 1. Right? This is actually the same arrangement as this one. If you don't believe that, right, draw it. Draw the table, and you'll notice that each of them have the exact same neighbors to their left and right. Okay, so this is the same arrangement of knights around the table. So then if we want this notation we're using to be unique, we should have the knight represented by the smallest number appear first in the list. All right, so have knight with smallest number appear first in the list so that we have uniqueness here, because otherwise we're going to be double counting. Okay. Then this tells me that an arrangement of knights at the k tables So an arrangement of knights at these k tables is then uniquely represented by a list of k strings of integers in parentheses. By a list of k strings of integers. So this is represented by a list of k strings of integers in parentheses, where each integer between 1 and n appears exactly once. So here's an example. Okay, so let's say that we have 6 knights in 3 tables. So 6 knights, 3 tables. Okay, so maybe let's seat knights 1, 3, 5 counterclockwise around the first table. Yeah, let's see, knights 1, 3, and 5 clockwise around table 1. Then we could have knights 2 and 6 at another table. And knight 4 at the last table. Then this arrangement is denoted by this. But of course, we already see this just is cycle notation for permutations. Okay, so this is a cycle notation that we use to describe permutation on 6 objects. And so in this way, there is fact, which is the seating arrangement of n knights at k tables corresponds. So a seating arrangement of n knights at k tables. This corresponds exactly with a unique permutation in this symmetric group on n letters having exactly k cycles. So a unique pi having exactly k cycles, and every such permutation corresponds to a unique seating arrangement. So this arrow truly goes back and forth here. And it goes, what I mean by the arrow goes back and forth is seating arrangement corresponds to a unique permutation. A permutation corresponds to a unique seating arrangement. There's no ambiguity here with the notation we've developed. So this is, I can go back and forth here. This is truly a one-to-one correspondence. These are the same counts of objects. Okay. And so this gives us characterization of these sorts of numbers. So, definition. These are called the Stirling cycle numbers, or Stirling numbers of the first kind. So the Stirling cycle numbers, what are they? This is the notation we use, so it's like the notation for a binomial coefficient, except we're using square brackets instead of big parentheses here. So this is the number of ways to seat n nights at k round tables that are identical. This is by this previous fact, because these two things count the same. These are in one-to-one correspondence. This is the number of permutations pi in S sub n having exactly k cycles. These are called unsigned Stirling numbers of the first kind, or Stirling cycle numbers let S of nk be defined to be minus 1 to the n minus k times this associated Stirling number. This is called the signed Stirling number of the first kind. Okay. We're mostly going to be concerned with the unsigned ones, but there are reasons to talk about the signed version. They have various nice algebraic properties, but we're mostly focused on the unsigned ones. Okay. So let's compute some of these. So let's do some specific examples here. Well, how many ways are there to seat n nights at 0 tables? Well, none unless there are 0 nights. So this is 1 if n is equal to 0. So vacuously we'll say there's one way to seat 0 nights at 0 tables, and 0 otherwise. So if there are a non-zero number of nights, then there are 0 ways to seat those nights as 0 tables. That makes sense intuitively. What if there's 1 table? Well, we have already actually computed this. The way to seat n nights at 1 round table was the first example of a counting with symmetry argument that we made. And we found that this was n minus 1 factorial, and that's true for n greater than or equal to 1. Okay. What about if there are n tables? If there are n tables, then every night would have to sit at their own table, because we can't leave any tables empty. So I would not be allowed to have, say, 2 nights sharing a table in that instance, because that would leave at least 1 table empty. right? So this is 1. What if there are n minus 1 tables? What if there are n minus 1 tables? If there are n minus 1 tables, then I have I don't have enough tables that every knight gets their own table. I have one less than that. So I know that by the pigeonhole principle, for instance, at least one of these tables is going to have 2 knights at it. But in fact, that's exactly what's going to happen in all cases, because all of these tables can't be empty. None of them can be empty. So that is exactly the situation that is completely general in this case. And so really, this is a way of choosing the 2 that are going to share the table, right, from the n. And so this is n choose 2. Okay. What if there are more tables than knights? What if k is bigger than n? Or what if k is negative? Does that make any sense? We're not going to talk about a negative number of tables, and if we have more tables than knights, I can't do this in a way that no table is empty, and so this is 0 in this instance too. One more thing we have, which we could say, well, there's a correspondence between seating arrangements and permutations here. And so if I were to count all of the numbers of permutations in my symmetric group in letters or in numbers in objects having exactly k cycles, if I let k go, from if I just sum over all k, but if I let k go from 1 to n, for instance, right? Then what I get is a sum over all the permutations having any number of cycles. So this is the total number of permutations, but the total number of permutations in S sub n is just n factorial. So these have to be the same. These count the same objects, which are just all permutations. And so we have this fact as well, that a sum over k of the Stirling cycle numbers is actually n factorial. Okay. Now, these are some specific values of this. To generate the full table, we're going to need something nicer. We're going to need more. To see how this is going to work, let's consider another specific example. Let's let n equal 4 and k equals 2. Okay. So, suppose one knight arrives late. Suppose one of the knights arrives late. This is a frequent, should I call it a trick? More like a technique. This is a frequent technique used when we're counting something that involves like an arrangement. We're thinking of it in terms of people. So we say, yeah, someone gets in late. And the question is, how do I insert them into the existing arrangement, right? i.e., we have already arranged 3 knights. So how can we insert the last person, the latecomer? Now, one thing to note here, right? When we say we've already arranged 3 nights, note it's okay at this step if there's an empty table. Well, here there's only 2 total tables, so why is it okay? So when I say that I've arranged 3 nights here, I don't mean that I've arranged them relative to all of my rules, because not all of them have been seated, right? There's still one person left. So it's okay if this, maybe we should call this a partial arrangement, right? Partial. We've partially arranged these nights because maybe the configuration I have at that stage doesn't satisfy what it needs to in the what I'm considering a full proper seating configuration. But after the last night gets there, whatever results after I seat that night, that has to follow my rules. That has to be a proper seating arrangement. The reason I'm going through this is because, okay, think about how we have done this, right? So let's say that I have so I have 2 tables here, right? Let's say that the first 3 nights are all seated at the first table. So this table is empty. Well, when the 4th night arrives, he only has one option. He has to go here. Right? There's no other option. So this is one way that we could do this. Okay. So so then what is the number of arrangements if this is the case? So this is we'll call this case 1. In this case, what is the number of total arrangements? Well, really, I'm forced to insert the 4th night at this table. Okay? So the number of total different ways to do this, at that last step, I have no choice. I am forced to put the last night at the empty table. And so that is really not contributing to my count here. What's really contributing to my count is the number of different ways to arrange these first 3 nights, right, at the first table. But that is just this, the Stirling number 3-1. This is the Stirling cycle number 3-1. And of course, there's 2 ways of doing that. Okay, so this is the number of arrangements of the 4 nights is actually just the number of arrangements of the first 3 nights at the first table, because there's nothing going on to assign the 4th night. The 4th night always goes to the second empty table, so there's nothing happening there. The number of ways to do this then is going to be the number of ways to arrange the 3 nights at the first table, which is computed by this Stirling number. Okay. There's another case that looks something like this, right? So 2 nights are seated here. I'm labeling them 1 and 2 after the fact. The 3rd night is seated here. And now I have a choice. Right? The 4th night can go here or here. Now, the 4th night is not forced to go to the empty table to make the rules be satisfied. The 4th night is allowed to go to either of these tables. Okay. Let's see how many ways there are to do that. So, so what do I do? So, 2 of the nights here, 1 of the nights are at the other table. You can join the single night. So how many ways can I join the single night? Well, I mean, really, like there's only one way. However I join the single night is going to give the same configuration. But how I join the other 2 nights, there are 2 ways to do that, because I could sit either here or here, right? On the left of one or the left of the other, right? So those are the options. There's two in that case. So regardless, all taken together, the number of arrangements of fortnights is 3 times the number of ways to seat 3 knights at 2 tables, which is the total. There, like I said, there are 3 options here, 1 and 2 options here, so that's 3 options, and then the what I'm counting on top of that, or in addition to that, is the number of ways to seat 3 knights at 2 tables, which is the number of different ways that these first 3 knights could have been arranged, right? Because I'm showing you one particular arrangement, but of course, knights 2 and 3 could sit here, and knight 1 could be the solo knight, right? Any of these 3 could be the solo knight at the table, right? And so it's 3 times the Stirling number 3-2 here. Stirling number 3-2 is 3. Again, to see that the Stirling number 3-2 is 3 is any of the knights could be the lone knight. That is the way of counting, right? It's the configuration is entirely determined by which knight is the lone knight. So you could have knight 1 as the lone knight, knight 2, or knight 3. 3 possibilities. Okay, because the remaining table is going to be the same. There's only be one way to arrange that once you've chosen. So choosing which knight is sitting alone at the table for the first 3 knights. That is just the way to enumerate this. So this would be 3 times 3, or 9 total arrangements. Now, these 2 cases enumerate everything that goes on in this situation, and so the total number of arrangements of 4 knights at 2 tables. This is the Stirling number 4-2. This, just by what we have written here, is 3 times the Stirling number 3-2 plus the Stirling number 3-1. Well, it turns out that if you want to actually see the full, we just computed this was 9 and this is 2, so this should be 11. There are 11 such arrangements. If you want to see those 11 such arrangements, here we go. So this is an arrangement of the 4 knights, Bedivere, Percival, Lancelot, and Tristram. So Tristram, Bedivere, Lancelot, and Percival arranged at 2 tables. Here you go, such that no tables are empty. There's the 11 possible configurations. That's all of them. Now, why did I count it in this way? You may have already been telling yourself, well, this isn't simply something that will work in this instance. This actually works in general for general n and k. I just have to be careful with how I write this, but let's see how this works in general. So this process, this method leads to a very nice recurrence relation. Okay, what is the recurrence relation? So to seat n knights at k tables, we can first seat n-1 knights at k-1 tables. then put the last night at the last table. Or we can seat the first n-1 nights at k tables. So not leaving a table empty here. Okay, and then insert the last night at one of these tables. Okay, this night must sit on the left side of one of the other n-1 nights. So this night sits on the left side of some night. One of the n-1 nights already seated. So there are n-1 ways, or I should say n-1 different places to seat. To seat the last night. In that second case. Thus, what did we just say? The number of ways to seat n nights at k tables can be done by, there are n-1 different places to seat the last night. After the n-1 nights have been seated at k tables, so that is n-1 ways that I could do that times n-1 k as a Stirling number, so this is the number of ways to seat n-1 nights at k tables. Or I could seat n-1 nights at k-1 tables and insert the last one at the kth table, which gives me no choice there. So this is n-1, k-1. So Stirling number n-1, k-1. Notice that this general recurrence relation matches with what we had here. So there it is. Okay, we can use this to generate a Stirling triangle like we did for the binomial coefficients, or similar to Pascal's triangle. Because really the reason it could be generated relied on a similar recurrence relation using binomial coefficients. So we can use this to generate a Stirling triangle. If you want to see what that is, here's the table. Notice on the right-hand side, we are taking the sum across the rows, which is the sum across the k's, right? For a fixed n, it's a sum across the k's. But we already showed that a sum across the k's gives us n factorial, because ultimately these are counting the number of permutations in S sub n having exactly k cycles. So summing across all of k is including all of the permutations, and the number of permutations in S sub n is n factorial. Right? The number of permutations of n objects is n factorial. So going back here, here is our table of cycle numbers. The sum across the rows now is n factorial. Okay, for fixed n, summing across the k's. Okay, well, now we see this recurrence relation. Of course, when we have recurrence relations, what is our thing to do? What has been our approach to these of late? Well, since we've had generating functions, the idea is to use a generating function. So, of course, recall that by the binomial theorem, the generating function for the sequence of binomial coefficients has a really, really nice form. So if I'm looking at that generating function of the binomial coefficients, this is, of course, just x plus 1 to the n. Okay. Let my generating function, I'll say g sub n of x. So I'm fixing n, and I'm letting this be the generating function for these Stirling cycle numbers. Okay. Note, of course, that g naught of x is just the constant 1 for n greater than or equal to 1. What do we have? Why do I care of peeling off that term? Well, of course, the reason I care is because this recurrence relation holds for n greater than or equal to 1. So holds so long as n is greater than or equal to 1. So in this instance, my g sub n of x, which is defined this way, sum over k of my Stirling cycle numbers, x to the k. What is this? This is n minus 1 times the sum over k of Stirling number n minus 1k x to the k plus the sum over k of Stirling number n minus 1k minus 1 x to the k. This is just applying the recurrence relation here. So using this for n greater than or equal to 1 for my coefficients in this generating function, this is what I get. Of course, I do this so that I can notice that there's this self-referential recurrence thing going on here where this is actually just the generating function for the same quantity except for n minus 1. And this, I can do the thing I always do, re-indexing here, so I can pull a copy of x out, which makes this x to the k minus 1, so that this is actually re-indexing. This is exactly just the generating function for n minus 1 as well, or the generating function g sub n minus 1. So this is n minus 1 times g sub n minus 1 of x plus x times g sub n minus 1 of x. And so solving for this, or rather simplifying this by combining these two, this is saying that g sub n of x is equal to x plus n minus 1 times g sub n minus 1 of x. Okay. Now, here, use induction. Using induction, I'm not actually going to do the argument, but using induction, you can show that what this means is that g sub n of x is actually, starting with g naught of x being 1, this is x to the k rising, or sorry, x to the n rising. This is x times x plus 1 times x plus 2, and so on, all the way out to x plus n minus 1, which is exactly x to the n rising. Thus, x to the n rising is this expression, this generating function, where the coefficients here are these Stirling cycle numbers. Okay. And this is true for n greater than or equal to 0. And therefore, what this tells you is that the Stirling cycle numbers allow us to express rising factorial powers as linear combinations of ordinary powers, right? So allows us to express rising factorial powers as linear combinations of normal powers. Okay. There are relationships here. We can actually do this for falling factorial if we use the signed Stirling numbers. So can also do this for falling factorial powers using the signed Stirling numbers. Okay, but I'm not going to do that. But you can look that up. This is on page 231. That last thing I mentioned is on page 231. This is exercise 7 if you wanted to have a look at it. Okay. So that is that. Got a little bit more time today, so I'm going to keep going. That is our discussion of the Stirling cycle numbers. So now, another question. How many ways are there to divide n guests at a party into exactly k groups if we disregard the arrangement of people within each group? So how many ways are there to divide n guests at a party into exactly k groups if we disregard the arrangement of people within each group? So, I'm going to ask a second question, which is, how many ways can I partition a set of n objects into exactly k non-empty subsets so that each element in the original set appears exactly once among the k subsets? So how many ways can I partition a set of n objects into exactly k non-empty subsets in a way that each element in the original set appears exactly once among the K subsets. So each element gets put into some subset. None of the subsets are empty, but not just put into at least one, it is put into exactly one. If it's put into one subset of the K subsets, it will not be in the others, right? Because of course a set, subsets of a set, you can have as much overlap as you want, right? So this is a special thing. It's clear that these two questions are the same question. I've just rephrased this one to be something you would ask to people at a party versus something you might ask to someone a little bit more mathematically in tune with what's going on, right? I've just stripped out this language a little bit, but this has the same intuitive thing. Like these are the same two questions, right? But this makes it easier for us to see maybe how to approach this. So for instance, let's do an example. Let's say we have the set of three elements, ABC, and I want to partition it into two non-empty subsets. So how many ways to partition into two such subsets? When I say such, I mean satisfying this question. Well, I could do the subset AB and then put C by itself. I could do A and C together and then put B by itself. I could do B and C together and put A by itself. And that's really it. Okay. How many ways into one subset? So the answer to this question is 3. How many ways to partition into one subset? Well, just one. That's the only way. Okay. How about into 3 subsets? Well, I only have 3 elements, so that's it. That's all I can do. So there's also just one way to do that. Okay. And so this leads us to another class of numbers. Stirling set numbers. What are the Stirling set numbers? So we will denote this by the following. We use squiggle brackets to denote these. These are the number of ways to divide in objects into exactly K groups understanding our setup, the rules that have to be followed. All right. These are the Stirling set numbers. Or the Stirling numbers of the second kind. You will see this oftentimes in the literature represented as S of nk. That's fine as well. Let's, as we did with Stirling numbers of the first kind, let's compute a few of these. So we've already seen the number of ways to divide n objects into one group is the same as the number of dividing n objects into n groups, which is 1. There's just one way to do both of those things. Okay. This is true for all n greater than or equal to 1. So what about dividing them into 0 groups? Same as for Stirling numbers of the first kind. If n is 0, we'll say that there's one way to do this. If there are no objects. Otherwise, this is 0. So obviously you're going to be more often in this case. Okay. What about the number of ways to divide n people into n-1 groups? Well, again, what you have done here is how you have done this is just like with the tables question. Now you don't have enough groups to match every person to their own group. So now you have a choice. You choose 2 people that get put into the same group and the rest get put into their own groups. Okay. So this amounts to the number of ways to choose 2 people from the n, which is, of course, just n choose 2. Similar to previous things, this is going to be 0 if k is negative or if k is greater than n. If there's more groups than there are objects to put into groups, then can't do this in a way that they're non-empty. Okay. Also, note the following. What is the relationship between the Stirling numbers of the first kind and the Stirling numbers of the second kind? That is the Stirling cycle numbers and the Stirling set numbers. What is this counting? This is distinguishing among the different ways to arrange the n people within k groups, but this does not. So they all get counted the same here, but they don't here. They get distinguished amongst the groups. And so we have this bound, and that is true for all n greater than or equal to 0, for all k. Lastly, I want to try to do the same thing that I did for Stirling numbers of the first kind to try to see if there's an analogous thing I can do for Stirling numbers of the second kind. So, suppose we divide n people. We'll say n is greater than or equal to 1, into k groups. Okay. At a party. But we know one person will arrive late. So again, we are doing this arriving late trick. to see, which is really all this is just peeling off the last thing. It's forming a configuration by pretending that you already did the thing for the first n-1, and then you're tacking on the last person to arrive to get a configuration that follows the rules. Okay, so we could divide the first n-1 people that are not arriving late into k-1 groups. Then place the last person into the kth group when they arrive. Or we can arrange the first n-1 people in k groups then pick a group for the last person to join. But then in the first case, how many ways are there to arrange the guests? Well, the Stirling number of the second kind, n-1, k-1. In the second case, how many ways are there to do this? Picking a group, there are k groups to pick. So this would be k times the number of ways to do this for n-1 people into k groups. So k times the Stirling number of the second kind, n-1 k. But this is either or, this or operation, so I add. And so this implies that my Stirling set number is k times the Stirling set number of n-1 k plus the Stirling set number n-1 k-1. Okay. And this is for n greater than or equal to 1. So that I get, again, nice recurrence relation. Which again allows us to compute a Stirling triangle of the second kind. To see this. Here is the Stirling second kind triangle. So we see the sums across the rows here are denoted by this b sub n. We will do something with this later. This was what we'll do in the last lecture tomorrow. These are Bell numbers, so we'll talk about those in a little bit, but I just wanted you to see the table for now. Okay. And so we'll start here tomorrow when we finish up our discussion of Stirling numbers of the second type and move on to Bell numbers and maybe even Eulerian numbers if we get that far. But that we'll likely be ending our discussion of these things with bell numbers. And like I said, maybe a tiny bit on Euler area numbers, or maybe I'll talk a little bit about partitions. One of those things I haven't decided on yet, but then you will have seen all the material that the course has to offer. So we're beyond in the home stretch. We got one more lecture. So anyway, we will see tomorrow the final bit of material. So I will see you all then.